Hello, everyone. My name is Angela Lee, and I am an undergraduate researcher working with Dr. Anthony Cozzolino and Dr. Shiva Malavan in the Department of Chemistry and Biochemistry. This year, my research focus has been utilizing Pnictogen bonding to synthesize self-assembling structures. So the chemical at the center of this study is called chlorantimony 3,5-ditert-butyl catecholate. Throughout the presentation, I'm probably just going to refer to this as R chemical for short. So similar to the way that DNA uses hydrogen bonds to self-assemble, compounds containing antimony, denoted by the chemical symbol Sb, can use Pnictogen bonding to self-assemble as well. When antimony bonds with a polar element such as chlorine, positive regions called sigma holes form opposite from this polar bond on the antimony atom. These positive sigma holes interact with negative charges to form Pnictogen bonds. In this study, we focused on chlorantimony 3,5-ditert-butyl catecholate and its interactions with nitrogen donors. So the supramolecular structures that we studied use Pnictogen bonding, the process I just described in the previous slide, to self-assemble in a consistent and predictable way. This property of molecules that contain heavy Pnictogens like antimony has a variety of applications that impact the real world. One type of technology that relies on self-assembly is self-healing polymers. Supramolecular polymers are composed of monomers that self-assemble using non-covalent forces, such as Pnictogen bonds, and can be broken apart using mechanical force. This reaction is reversible, and the polymer can reassemble once the mechanical force is removed. Self-healing polymers keep materials from becoming damaged over time. Another application for Pnictogen bonding is charge transfer and information storage. DNA uses hydrogen bonds to hold together strands containing the genetic information of an organism. Pnictogen bonds are similar to hydrogen bonds, so this could be another possible use for this type of chemistry. And finally, Pnictogen bonding could also potentially be used for drug delivery inside the body. Some compounds that have the ability to Pnictogen bond form micelles, which are supramolecular assembly of molecules with a space in the center. When certain Pnictogen-containing compounds are sonicated, micelles form and trap material inside. With further research, this phenomena could be applied to medicine to improve drug delivery in the body. Before we can begin studying how our chemical interacts with nitrogen donors, we have to synthesize and study the chemical itself. The sigma holes on any chemical can be located through charge mapping. Blue indicates positive regions and red indicates negative regions. And the shade indicates how strong the bond will be. So for example, the lighter the shade of blue, the more positive that region is. So if you look at the figure on the left, you can see a large light blue region, which indicates that there's a sigma hole on one side of the antimony on the opposite side of the atom from the chlorine. Antimony, as well as most Pnictogens, forms weak but stable interactions with nitrogen donors at sigma holes. So to synthesize our chemical, we tried two methods. Method 1 involves mixing 3,5-ditert-butyl catecholate with a compound containing 1 antimony, 1 chlorine, and 2 ethoxy groups. The second method instead uses antimony trichloride. All the reactions were performed inside a glove box in a nitrogenous atmosphere because the products will decompose if they're exposed to oxygen. For both methods, the reactants were mixed and stirred at room temperature for around 3 hours. Method 1 was deemed most successful because it yielded the cleanest product. To confirm that we made the desired product, we obtained a proton NMR spectrum of our product. Looking at the spectrum on the right, we observed 2 peaks with 9 protons each on the right, confirming the presence of 2 tert-butyl groups. We also observed the 2 toluene peaks in the center and 2 aromatic peaks on the far left, containing 1 proton each, as we expected. After confirming that our product had all the expected protons, we obtained the crystal structures through X-ray crystallography. So looking at these crystal structures, we observed that in high concentrations, the molecules formed pairs called dimers, and these dimers stack together to make a staircase-like formation. It is important to know that this chemical dimerizes at certain concentrations so that we can properly dilute our chemical when we add the nitrogen donors to form Pnictogen bonds. If we use too high of a concentration, it may be difficult to observe how our chemical interacts with the donors because it may be interacting with itself as well. After fully characterizing our chemical, we co-crystallized our product with several nitrogen donors, including 2,2-bipyridine, 3,3-azopyridine, phenanthrene, terpyridine, and 4,4-azopyridine. We chose both bidentate and tridentate donors to see how this would affect the angles and the locations of the Pnictogen bonds formed. One of the most interesting crystal structures that we observed was the co-crystallization with terpyridine, our tridentate donor. Terpyridine is tridentate because it interacts with our chemical in 3 places, as you can see in the structure on the left. The Pnictogen bonds are shown by the dotted lines between the purple antimony atom and the blue nitrogen atoms. The location of these 3 bonds shows where sigma holes appear on the antimony, and the bond lengths, which are labeled, indicate the strength of each sigma hole. The shorter the bond length, the stronger the interaction. So it's a little bit difficult to see in 2D, but the shortest bond observed is the closest to being exactly opposite from the electronegative chlorine atom, which we expected. So observing these results, we conclude that when a pnictogen, such as antimony, is bonded to a highly electronegative element, such as chlorine, a large sigma hole will form on the antimony across from the electronegative chlorine. This sigma hole interacts with multidentate nitrogen donors to form weak but stable interactions, which we call pnictogen bonds. In the solid state, our chemical will self-assemble into dimers and staircase-like structures, always bonding at the same places in a predictable way. This self-assembling property of pnictogen-containing molecules can be applied to several areas, including the synthesis of self-healing polymers, as well as other applications that I mentioned earlier. So currently, we are continuing this area of research by studying the interactions between our chemical and nitrogen donors, specifically in solution rather than solid state. We're experimenting with titrating the nitrogen donors into our antimony-containing chemical, both dissolved in toluene, and observing the UV visible spectrum. We measure and chart the absorbances throughout the titration as pnictogen bonds form, and study the trend as the concentration of nitrogen donors in the solution increases. We hope that we can use this information to further characterize pnictogen bonding properties. I'd like to give some quick acknowledgements. I would like to thank the Honors College Undergraduate Research Scholars Program supported by the CH and Helen Jones Foundations. And I would also like to thank Dr. Daniel Unruh for his assistance with X-ray crystallography, which y'all saw throughout this presentation. Thank y'all so much for listening to my presentation, and I hope you enjoy the rest of the conference. Bye-bye.